Hello, welcome to Scholar Fedu. This is our UTME prep series where we provide relatively detailed solutions and explanations to the UTME questions. And in this recording, we're looking at UTME questions for chemistry for the year 2013. This is the second part of the recording where we'll be looking at the last 25 questions for the year 2013. Before we continue, please don't forget to subscribe to our YouTube channel, like and share our content. You can also visit our website at scholar.com to pass the UTME exam and modular quizzes for free. Alright, first question here. In an endothermic reaction, if there is loss in entropy, the reaction will not be spontaneous. Okay, so the best measure of spontaneity in a reaction is the change in entropy. What by spontaneous is that when you say reaction is spontaneous, it means that reaction occurs on its own, okay, without the need for an external supply of energy in form of heat. Okay, so if the entropy is lost, if the entropy of this of the reaction medium of the species reaction, if it is lost, okay, then that reaction is not going to be spontaneous, meaning it will require some sort of energy to initiate that reaction. In the reaction above, the concentration of SO3 can be increased by decreasing the temperature. Now this reaction here, you can see the enthalpy change here is negative. It means that this reaction is an exothermic reaction. It's a reaction in which heat is given out. Okay, now for an exothermic reaction, if you want to favor the for an exothermic reaction, okay, a decrease in temperature will favor the forward reaction. It means that more of this will be produced, okay, or the concentration of this, what you have on this side here, is going to increase, while an increase in temperature is going to favor the backward reaction. This is the case with an exothermic reaction. But if it is an endothermic reaction, okay, that is a reaction in which heat is taken in or absorbed, increasing the temperature is going to favor the forward reaction, but decreasing it would favor the backward reaction. However, this is an exothermic reaction. Decreasing the temperature is going to favor the forward reaction, meaning the concentration of this sulfur 6 oxide here is going to increase. The minimum amount of energy required for reaction to take place is that defines what we call the activation energy. It's also called the energy barrier of a reaction. It is the minimum energy that is needed for a reaction to proceed. In the graph above, the activation energy of the catalyzed reaction is, so the activation energy of the catalyzed reaction is going to be reduced. Okay, what catalyst does in a reaction is it reduces the activation energy. Okay, so how do we find the activation energy for the catalyzed reaction now? All right, we then look at it is this. Look at this diagram here. All right, without catalyst, this is the activation energy from here to here. Okay, we look at the level of the reactants here and the activation complex here. Just trace it down to this axis and take the difference. This is for without catalyst, but with catalyst it will be from here, the difference between here to here. Okay, that is from here, whatever you have here, minus whatever you have here. So if you go here now, this is it. This is activation complex with the catalyst. If you trace this down, this is 200 here, while here is 100. So you have 200 minus 100, and that is 100 kilojoules. Okay, that is 100 kilojoules. 2-methyl-butanol oil is an example of a primary alkanol because it has only one alkyl group attached to it. Okay, it has only one alkyl group attached to it, so it is a primary alkanol. Primary alkanol, they generally have the formula ROH. Okay, so this is a primary alkanol. The equilibrium constant K of the reaction above is represented as. Alright, so for that we are going to take the concentration of the product over the concentration of the reactant. Let's say they give us a reaction like this, a reversible reaction similar to what you have here. Alright, but let's do something simpler like this. So A moles of P reacts with B moles of Q to produce C moles of R plus D moles of S. We say that the equilibrium constant is equal to this R raised to power X times D raised to power X. Okay, that's on the product side. R raised to power C rather times S raised to power D divided by what you have on the reactant side, P raised to power A plus Q raised to times Q raised to power B. So if you relate that to this reaction there, all right, that means that we start with the product side. So it will be Fe3O4 raised to power 1, which will just be Fe3O4 plus H2 raised to power 4, okay, plus H2 raised to power 4 over Fe raised to power 3, okay, Fe raised to power 3, this should be superscript, plus H2O raised to power 4. So that's all we have here. In the laboratory preparation of ammonia, the flask is placed in a slanting position so as to, this is to prevent the condensed water, okay, the condensed water which is still hot, from breaking the flask, the reaction flask. Which of the gases is employed as an anaesthesia? So anesthesia are substances that are given to patients, okay, doing surgeries, especially to reduce the pain that they will feel, okay. And an example of such substance that is used is dinitrogen oxide. Dinitrogen oxide, or what is known as laughing gas, is used as an anesthetic during surgical operation. Sulfur 4 oxide is a strong reducing agent in the presence of water due to the formation of trioxosulfate, okay, trioxosulfate 6 salts. A metal that forms soluble trioxosulfate 4 ion is, the trioxosulfate 4 ion of potassium is soluble in water, okay. It is soluble in water but not in solutions of potassium hydroxide. And we are talking about the solubility. Of course, we are looking at its solubility in the universal solvent, which is the water. We have a website at scholar.com where you could practice exams for free, the UTME exam and the post-UTME exam. It also features modular quizzes in physics, chemistry, and biology. So if you've studied a topic in any of the subjects and you want to test your understanding of the topic, you can head on to our website at scholar.com and take modular quizzes for free. Also, if you sign up on the website, it has a personalized dashboard where you could use to check your progress in learning. We also have interactive sessions on the website and on our social media platform. Freebies are also available to top performance on the website. Next, copper is displaced from the solution of its salts by most metals because it's, now for a metal to be displaced by another metal, then the metal that is displacing the other one must be more electropositive. So the reason why copper is displaced by is displaced from solution of its salt by most metals is because it is lower in what we call the activity series. The activity series is the series of metal that's like from the most reactive to the least reactive of the metals. So if you look at that series here, you have potassium, sodium, calcium, magnesium, aluminum, zinc, iron, tin, lead, hydrogen. You see that copper is way down in the series. That's why most of these metals I have here, before it, okay, they will displace it from a solution of its salt. So copper it has more metals above it in the activity series. So it is at the bottom. You can see it's at the bottom or close to the bottom, not exactly at the bottom, okay, but close to the bottom of the activity series. The colored nature of transition metals is associated by their partially filled transition metals, okay, they have partially filled d orbitals, okay, which accounts for many of the properties that they have, like the formation of the colored nature of their ions, okay, also the formation of complexes, and they are used as a catalyst. Aluminum containers are frequently used to transport triazonides 5 acid because aluminium, that is because aluminium is passive with triazonides acid, meaning it does not react with the acid. Okay, the aluminum is passive, it does not react with the acid. What happens is that the aluminum is going to form a protective layer of its soil of its oxide. Okay, it will form a layer of its oxide, which now inhibits any further reaction with the acid. The reaction between ammonia and ethyl ethanoate produces, when ammonia reacts with ethyl ethanoate, it will form ethanol and ethanamide. Generally speaking, the reaction between an ammonia and an alkyl alkanoate is going to produce an amide. Okay, like this ethanamide here, it will produce an amide. The decarboxylation of ethanoic acid will produce carbon dioxide, and carbon dioxide is carbon dioxide, that is CO2. Now the general formula for ethanoic acid is RCOOH. Okay, RCOOH. Now if you decarboxylate it, all right, that if you remove the carboxyl group, all right, and carbon dioxide is released from it, that means you are going to have CO2. This CO2 is removed from it, so the remaining thing you are going to have is just RH. Okay, it's just RH. For ethanoic acid, for example, ethanoic acid has general formula CH3COOH. Okay, CH3COOH. If you remove COO from it, that's carbon dioxide, what you are going to have left is CH4. Okay, you'll be left with CH4, so that will be methane. The compound above is an going by the functional group that we have here. Okay, this compound here is an alkanon. Okay, it is an alkanon. Okay, that's the general formula. R, this CH3 is R, is an alkyl group. This CH is also another alkyl or alkyl group. So we have CH3 COCH3. Okay, so it's like saying this is R and this is R prime, so you now have RCOR prime, which is the general formula for the alkanon. For the alkanols we have ROH. Instead of O, this will have been OH, and this will not be a double bond, it will be OH, and you still have another hydrogen here. The compound that reacts with sodium hydroxide to form salt and water is, that compound must be an acid. Sodium hydroxide is a base. Okay, so the something that will react with it to form salt and water must be an acid. Acid generally reacts with bases to form salt and water, and from the options here, the only acid that we have here is this. This is an alkanoic acid. This is propanoic acid. Okay, so it reacts with the sodium hydroxide as an acid to form salt and water. You can also join our online tutorial classes for different classes. We have tutorials for students in SS1, 2, or 3. We also have for UTME candidates, for JAMB candidates, for students who want to write the JAMB or the UTME exam, and for those who want to have the post-UTME exam after the UTME exam, and also for candidates that are sitting for WAEC exam or GCE or NECO. And we offer this tutorial on various platforms, so you could join us on WhatsApp or on Telegram, it could be on Zoom or on Google Classroom. So we have various platforms where we take our tutorial. The links to join the platform are available on our website at scholar.com, or you could also check it out in the video description below. Next question, use the following options above to answer this question. Which of the following compound in the solution will turn red litmus paper blue? So we know that the litmus paper is either red or blue. Okay, the litmus paper in an acidic medium is red. In an alkaline or basic medium, it is blue. Okay, now to turn a red litmus paper blue, then you have to put it in an alkaline medium. Okay, so the question here is to identify which of this compound in solution, the solution of which of this compound is going to turn red litmus paper blue. Is actually telling us to identify the base here, okay, or the alkaline that we have here, and that here is just the amines. Okay, amines are organic bases. Okay, and bases will turn red litmus paper blue. The general formula for the amines is RNH2. RNH2, where the R is an alkyl group. The dehydration of ammonium salt of alkanoic acid produces a compound with a general formula. Okay, it will produce an amide. Alright, it will produce an amide with the general formula RCONH2. RCONH2. Which of the following fractions is used as a raw material for the cracking process? That is diesel oils. Okay, diesel oil is used as a raw material in the cracking process. Other materials that are used include propane butane mix, a mix of butane and propane and butane. Naphtha as well. Okay, naphtha as well is also used as a raw material in the cracking process. The cracking process is a process by which large heavy organic molecules are broken down. Okay, are broken down into smaller units, usually under heat. Okay, under heat pressure or in the presence of a catalyst. An organic compound with a pleasant smell is likely to have a general formula. That compound must be an alkanoate. Okay, alkanoate or an ester. Because we say ester or alkanoate. So alkanoates, they have a characteristic sweet smell, and the general formula is RCOOR prime. Okay, where this R is CnH2n plus 1. So this will be CnH2n plus 1 COO CnH2n plus 1. Okay, these alkanoids, they are derived from esterification reaction between an alkanol and an alkanoic acid. So when an alkanol reacts with an alkanoic acid, an ester or alkanoate is formed with water. A primary amide is generally represented by the formula. A primary amide has only one radical. Okay, has only one radical, one alkyl group. So the general formula is RCONH2 for primary amides. Okay, for primary amides. So there will be only one of this here, RCONH2. The IUPAC nomenclature for the compound above is, that is this compound here. Now, how do we name this compound? The first thing we need to do is locate the longest continuing carbon chain here. Okay, how? We count the carbon chains. I can count in many ways. I can count from here. Okay, I can count in. Let's see. We now look at which one is the long. Which one we got the longest number? I can count as 1, 2, 3. Okay, so I have 3 carbon atoms. I will now treat these ones as like substituents. Sorry, we need to feature this double bond here. Okay, this double bond here has to be featured. Okay, so if I count from here, I will have 1, 2, 3, 4, 5. If I count, I can also count 1, 2, 3, 4, 5. Okay, now it means that this compound in question has the parent compound there has 5 carbon in it. I mean, it has 5 carbons. Okay, now of course, in naming an organic compound, the number of carbon determines the surface. Okay, determines the surface of the parent organic compound. Okay, the parent compound. So here, since we have 5, that will be pent. Okay, it's going to be pent because the number of carbon on the longest continuing carbon chain is 5. Okay, now pent what? Is it pentene or pentine or pentane? It will be pentene because of this double bond here. Okay, this double bond here tells us that this compound here is an alkene, and alkenes, their names end with what? ENE. Okay, so this will be pentene. Now pent what? Is it pent 1, pent 2, pent 3? If I count this carbon atom for me, I'm going to have 1, 2. That means the double bond is going to be between 1 and 2. Okay, the first and the second carbon atom. If I count from here, it will be 1, 2, 3, 4, 5. It means it will be between the 4th and the 5th carbon atom. I will take the one that will give me the lesser number. That is counting from here. Okay, so if I count from here, I'm going to have if I count from here, rather. Okay, what we need to consider to the time where we are going to count is this substituent here. Okay, if you are taking this as a substituent and this as like the parent chain, then I have to count from here. So I'll say 1 2 3 4 5. So we say the double bond is between the fourth and the fifth carbon atom. So this is going to be pent 4 in. So already from the option I can see this is the only pent 4 in that I have here. Alright, so I can go with this directly. But let's continue. So we say this is a substituent, this CH3, and this CH3 here is methyl. We now look at which carbon atom is it attached to. Okay, it's attached to the second carbon atom here. Okay, the second carbon atom. So we say this is what? 2 methyl. 2 because it's attached to the second carbon atom. Alright, if this was not here, if this methyl was not here, let's say this is just H. Okay, then we will have counted the carbon atom from here to take the lesser number for the double bond. Okay, but because we give preference to that substituent. Okay, we give preference to it. So this is going to be 2. Okay, so you have 2 methyl pent 4 in. Final question here. An organic compound contains 60% carbon, 13.3% hydrogen, and 26.7% oxygen. Calculate the empirical formula. We have the atomic masses of carbon, hydrogen, and oxygen. Alright, the percentage composition of the carbon is 60, of hydrogen is 13.3, of oxygen is 26.7. What we are going to do here is this. We will divide these percentage compositions here by the atomic masses of the element. So for carbon we have 60 divided by its atomic mass, which is 12. 60 divided by 12, that is 5. For hydrogen, 13.3 divided by 1, okay, its atomic mass, that is 13.3. While for oxygen we have 26.7 divided by 16, and that is 1.67. The next thing we are now going to do is we will divide by the smallest ratio. Okay, we are going to divide 2 by the smallest ratio here, which is 1.67. Okay, if we divide by 1.67, 5 divided by 1.67 will give us approximately 3. 13.3 divided by 1.67 will give us 8 approximately. 1.7 divided by 1.7 will give us 1. So that means that this carbon here, okay, we are going to have 3 of it, 8 of hydrogen and 1 of oxygen. So the empirical formula for this compound, okay, for this compound that has this percentage composition is going to be C3H8O. Okay, don't forget to check out our playlist. We have different playlists. We have for full solutions to UTME or JAMB questions and in physics, chemistry, and biology. We also have for modular quizzes as well. Okay, we'll also have a playlist for post-UTME or post-JAMB exam, and also for crash courses in physics, chemistry, and biology. So don't forget to check out our playlist for the available videos. So that's it for this recording. Thank you very much for watching. Please don't forget to subscribe to our YouTube channel at ScholarFedu. Okay, like and share our content, and visit our website at scholar.com to practice UTME exam and modular quizzes for free. Thank you.